Welcome to Module 49 in a series of lectures on statistical quality assurance and statistical process improvement. We've been discussing so-called 2 to the p factorial studies. We've talked about generalities and notation, the defining of main effects, 2-factor interactions, 3-factor interactions, and so on. We've looked at the Yates algorithm, and now we're going to talk about doing inference in P-way studies in terms of deciding whether the output of the Yates algorithm or the fitted effects are really clearly bigger than the experimental noise, and therefore are going to likely to be reproduced if we were to take another data set, or we expect the effects to actually hold up in an application. What we're going to do is we're going to use the ideas of L's and L hats and margins of error using the ideas of Module 42. So as it turns out, the output of the Yates algorithm, the fitted effects in a 2 to the p factorial study are L hats. And we can use the basic method of estimating a linear combination of the long run means rather than the sample means presented in Module 42 to derive margins of error to attach to L hats that are in this case fitted effects for a 2 to the p factorial study. The basic formula turns out to be really clean. Any 2 to the p factorial fitted effect is an L hat, and based on it, a confidence interval or confidence limits for the corresponding theoretical effect are the fitted effect plus t-value times pooled S times 1 over 2 to the p times this square root that is very simple. That square root is the sum of the reciprocal sample sizes. In the case that data are balanced and all of the sample sizes are the same, some value m, this reduces simply to fitted effect plus or minus t-value pooled S times this square root of 1 over m common sample size times 2 to the p. And these formulas provide the necessary margins of error for judging whether fitted effects really clearly represent something other than noise, whether they clearly represent some non-zero real effects of the experimental factors. For example, in the pilot plant study, we had 8 samples of size 2. If we take those 8 samples of size 2 and take the sample variances, those sample variances were 2, 8, 32, 2, 8, 8, 2, and 1. They're based on samples of size 2, therefore they have sample size minus 1 equal to 1, or degrees of freedom 1 for each of those sample variances. So the pooled S is just their sum over 1 plus 1 plus 1 plus 1, and so on. That turns out to be 2.83 grams. The degrees of freedom associated with that pooled S, there are 16 observations overall. There are 8 different groups. So it's 16 minus 8 is 8, or put it differently, we get 1 degree of freedom from each of the 8 samples. That means that using a t-value that is the upper 97.5% point of the t-distribution with 8 degrees of freedom turns out to be 2.306. 2.306 times this pooled S times, in this case, the square root of 1 over 2, basic sample size is 2, times 2 cubed, we end up with a margin of error of 1.63 grams to attach to every fitted effect. If you go back to the previous module, we'll go back to module number 48 and look at the output of the Yates algorithm. What you'll see is that fitted A main effects were about 11, fitted AC two-factor interactions were about 5, and the fitted B main effects were somewhat smaller, but were bigger than this 1.63 value. What that means is the rest of those fitted effects are so small that they're smaller in magnitude than their margins of error. We don't really know whether, for example, the C main effect is positive, negative, or 0. And so really the only effects that are larger than this margin of error are these. This idea of using margins of error based on confidence limits to judge the detectability of factorial effects really is the best available method. It requires that someplace in the data set there's some replication so that a pooled S can be calculated. As a matter of fact, one doesn't have to have replication at every single set of conditions. So this is not really a particularly onerous requirement. If you can just get repeat observations at a few sets of experimental conditions, that's not as difficult typically as that's a lot better than leaving oneself with ambiguous results. That said, sometimes one has to do analysis of data from an unreplicated 2 to the p study. That's not the ideal situation, it's not a good situation, but it's worth taking a couple of minutes here to describe what the best available analysis is when one has no replication. And that is to rely on a principle of so-called effect sparsity. One hopes that nature is more or less simple, and that in trying to describe the behavior of a system with many factors, that really there are only a few effects, one hopes, that pretty much dominate and describe what's going on in that system. It's sort of a Pareto principle of effects. When that effect sparsity holds, a way to try to identify the few big effects is to do normal plotting of the output of the Yates algorithm. So take the fitted effects for the all-high treatment combination. Take the A2, B2, AB22, C2, and so on, and normal plot them. The idea is that if most of the effects are smallish, look like noise, then the ones that stand out by plotting off the line established by the majority, those are the big effects. So here are some fictitious, unreplicated 2 to the 4 factorial data. The reader ought to go off, or the listener ought to go off and apply the 4-cycle Yates algorithm to make sure that one can come up with these fitted effects from those unreplicated 2 to the 4 factorial data. What I've done then on the next slide is to normal plot these things. Okay, normal plot A2, B2, AB22, and so on. Not going to bother to normal plot, include the overall average, the y bar dot 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 dot. So the overall mean is typically not included. But we'll normal plot these, and here's what we get. We get pretty much a straight line here for most of the fitted effects, but A2, D2, and probably AD22 can be seen as plotting off the line established by the rest. So we're looking at A2, and we're looking at D2 and AD22. So they're the big things. 3, 2, 1. Everything else is substantially smaller, and that shows up then on this normal plot for 15 fitted effects from this fictitious data set. That's using the idea of effect sparsity and normal plotting of fitted effects to identify statistically detectable effects when one has no replication. This is a last resort. One really wants to analyze replicated data so that one has some firm basis for understanding how big experimental variation is. One has a real pooled S and therefore can make margins of errors for the fitted effects.